Electric multiple unit trains of classes 414, 415 and 416 are equipped with two power braking systems, the automatic air brake and the electro pneumatic brake. The first of these, the automatic air brake, forms the vital fail-safe brake and works on a principle established many years ago. An air pipe running the full length of the train, and known as the automatic air brake pipe, is charged at a pressure of 70 pounds per square inch when the brake is released. Each vehicle of the train is equipped with a storage tank, called an auxiliary reservoir, which is also charged at 70 pounds per square inch via a non-return valve from the automatic air brake pipe. So we can see that when the brake is released, 70 pounds per square inch of air is charged throughout the train and in each auxiliary reservoir. When the driver makes a brake application, he does so by reducing the pressure in the automatic air brake pipe. On each vehicle of the train, adjacent to the auxiliary reservoir, is an item of equipment called a triple valve. When the automatic air brake pressure is reduced during a brake application, the air in the auxiliary reservoir is allowed to flow into the brake actuating cylinders, thus applying the brake. This flow is proportional to the reduction in the automatic air brake pipe pressure, so that as the driver gradually reduces this pressure, each and every triple valve responds to this reduction by permitting air to discharge from the auxiliary reservoirs to the brake actuating cylinders. To release the brake, the driver once again charges the automatic air brake pipe to 70 pounds per square inch, which in turn recharges the auxiliary reservoirs to 70 pounds per square inch, and the triple valves permit the air in the brake actuating cylinders to exhaust to atmosphere. It is important to understand that with this braking system, the brake application is graduable in application only. Once a release is effected, it will always be a full release. Because the automatic air brake is applied by reduction of the pressure in the automatic air brake pipe, we can see that this brake will automatically apply if this pressure is reduced in any of the following circumstances. A passenger pulls the communication cord. The guard or other member of the train crew operates an emergency brake valve. The train accidentally splits into two or more parts. A flexible section of the automatic air brake pipe between two vehicles bursts. The driver releases his grip on the power controller, actuating the driver's safety device. The driver is also able to initiate a non-graduable reduction in the automatic air brake pipe pressure by selecting the emergency position on the brake controller. This position simply dumps the air pressure more rapidly and, therefore, gives a faster full application of the brake. We shall look at the positions of the brake controller in more detail later. Before a train is taken into service, the continuity of the automatic air brake pipe is tested by the train crew. This test involves the charging of the brake pipe by the driver from the head-end cab, after which the guard checks that 70 pounds per square inch is registered on the automatic air brake pipe gauge on the rearmost vehicle. The guard now discharges the pressure, thus applying the brake, and, at the same time, the driver opens the master switch, preventing the automatic air brake pipe from being recharged. The guard observes that, after closing his valve, the pressure does not recharge for a few moments. The driver now closes the master switch again, recharging the automatic air brake pipe. When the pressure again rises to 70 pounds per square inch on the rear-end vehicle, the train crew may consider the brake continuity test to be successful. This vital safety test, which is also carried out on every occasion that the consist of the train is changed, establishes that the automatic air brake pipe is continuous throughout the length of the train, and that no master switch is closed in any cab but the leading cab. The second of the power braking systems, the electro pneumatic brake, is not a fail-safe brake. A second air pipe runs the full length of the train and is called the main reservoir pipe. This pipe and the connected main reservoirs are charged at 90 pounds per square inch directly from the electrically driven compressors. It is from this source that the automatic air brake pipe is charged via a reducing valve and the driver's brake controller. However, this main reservoir pressure is also used for the electro pneumatic service brake. When the driver makes an electro pneumatic brake application, he energizes train wires that run the length of the train and are carried between vehicles by a 27-way electrical jumper. On each vehicle, electromagnetic valves permit air to flow from the main reservoir pipe to the brake actuating cylinders, thus applying the brake, and from the brake actuating cylinders to atmosphere in release. The maximum pressure that can be applied to the brake actuating cylinders is 50 pounds per square inch, and the pressure is continuously graduable between 0 and 50 pounds per square inch in both application and release. The electro pneumatic brake has advantages over the automatic air brake as a service brake. It is quicker to operate, acts simultaneously throughout the train, and has a more positive response to fine graduations in braking requirements, and is ideally suited to high-density commuter service where fast and frequent braking is the norm. However, we can see that any interruption in the electrical supply throughout the train, such as the rupturing of a fuse or the tripping of a protective circuit breaker, will render the brake totally or partially inoperative. It is for this reason that the electro-pneumatic brake is always superimposed over the automatic air brake, affording the driver the security of a fail-safe braking system. The electro-pneumatic brake is tested by the train crew on each occasion that the automatic air brake is tested. The driver makes a full service application from the head end, and the guard observes a reading of 50 pounds per square inch on the brake cylinder gauge of the rearmost vehicle. Now let's look at the actual operation of the two power braking systems. When a driving cab is opened up, the driver first unlocks the master switch by means of his master key. When this switch is moved away from the off position, an air valve below the driver's brake controller is opened. Providing that the brake controller is in the release position, the main reservoir will now charge the automatic air brake pipe to 70 pounds per square inch. On the driving desk, the driver has a duplex gauge indicating the pressures in both the main reservoir and the automatic air brake pipe. Adjacent to this duplex gauge is a brake cylinder pressure gauge. As the automatic air brake pipe pressure climbs to 70 pounds per square inch, we can see that the brake cylinder pressure releases. Before we actually move the train, let's have a close look at the 5-position brake controller with which these trains are fitted. The number 1 position is called release. When the brake controller is in this position, as we have seen, the automatic air brake pipe is charged to 70 pounds per square inch and the electro-pneumatic brake is fully released. When the brake controller is moved from position 1 towards position 2, the electro-pneumatic brake is gradually applied. Each small movement of the brake controller towards the number 2 position will increase the pressure applied to the brake cylinders until the number 2 position is reached when the full 50 pounds per square inch pressure is applied. Now, as the brake controller is moved back towards the number 1 position, each small movement will effect a reduction in the brake cylinder pressure. This continuously variable graduation in brake cylinder pressure is a feature of this type of electro-pneumatic brake and is known as self-lapping. During application and release of the electro-pneumatic brake, the distinctive sound of the electrical contactors can be clearly heard. When the brake controller is moved to the number 3 position, nothing appears to happen. However, any air pressure applied to the brake cylinders by the electro-pneumatic brake will be trapped there when the brake controller is moved to this position. Actually, the number 3 position, known as lap, is associated with the automatic air brake and is the neutral position for that braking system. We can see that as the brake controller is moved from the number 3 towards the number 4 position, air is discharged from the automatic air brake pipe, provoking an application of the automatic brake. If the brake controller is moved back to the number 3 or lap position, the discharge of air from the automatic air brake pipe ceases and the pressure in the brake cylinders is held steady. Further movement towards the number 4 position will again discharge air pressure from the automatic air brake pipe, causing a further rise in brake cylinder pressure up to a maximum of 50 pounds per square inch. Thus we can see that the movement of the brake controller between numbers 3 and 4 positions enables the driver to graduate the automatic brake application. However, when the driver moves the brake controller back to the release or number 1 position, all air pressure in the brake cylinders is discharged, and the automatic air brake pipe is, once again, recharged to 70 pounds per square inch. The number 5 position is called the emergency position. When the brake controller is moved to this position, the air pressure in the automatic air brake pipe is immediately discharged by a large port, resulting in a rapid build-up of brake cylinder pressure to a maximum of 50 pounds per square inch. When a driver selects the emergency position, he must leave the brake controller there until the train has completely stopped. Before moving to the power controller, let's just recap on the brake controller positions. Number 1. Release of both braking systems. Number 2. Full application of the Electro Pneumatic brake. Number 3. Lap, the neutral position for the automatic air brake. Number 4. Full service application of the automatic air brake. Number 5. Emergency. Once the automatic air brake pipe is fully charged, the driver may now move the reverser switch to either forward or reverse positions. However, in order to do this, he must first hold down the power controller handle. The power controller is provided with 4 positions, successively applying more power to the train motors. On this type of train, however, the power may not be successively reduced by moving the power controller back to a lower setting. To reduce the power applied to the motors, it is necessary to return the power controller to the off position, then reselect the required power position. The positions of the power controller are off, shunt, series, parallel, and weak field. A most important feature of the power controller is the driver's safety device. With the reverser switch in either the forward or reverse positions, in other words when the train is in motion, the driver must maintain hand pressure on the power controller handle. Should he fail to do so, the driver's safety device will instantly cut off any power to the train motors and rapidly discharge the automatic air brake pipe pressure, causing a full brake application. Now that we have examined the principles of the 2 power braking systems fitted to this type of train, let's join the driver in the cab on a run from London Bridge Station to Cannon Street, platform 3. We can see that the driver has only selected the notch 2 or series position on the power controller. Between London Bridge and Cannon Street, a speed restriction of 20 miles per hour is in force throughout. The driver now shuts off power, allowing the train to coast for a short distance. However, because of the curvature, it is soon necessary to reapply power, in this case to notch 1. As we clear Borough Market Junction, we can see that a tight right-handed curve is ahead. Inside the right-hand running rail is a check rail. The driver cancels the AWS indication for the cautionary signal. As we approach Cannon Street Inner Home Signal, we can see that it is cleared for entrance to platform 3. The driver takes power once again. As we make our approach to platform 3, power is shut off for the last time. Entering platform 3, which is approximately 650 feet long, the driver makes a further light brake application of the EP brake and then releases, permitting the train to coast up the platform line. As the buffer stops are approached, a final series of EP brake applications are made to bring the train to a stop. Just before the moment when the train becomes stationary, the brake controller is moved back to the release position so that the actual point of stopping occurs with a reducing brake pressure. This final action prevents the train stopping with a jolt. The driver now blows down the automatic air brake pipe and opens the master switch, thus closing down the cab. Now let's rerun the last stages of the trip, the actual entry into Cannon Street Station, and simulate a fault on the Electro Pneumatic brake. To the right of the gauges on the driver's desk is a green lamp indicating that the electrical supply to the Electro Pneumatic brake is good, and the brake, therefore, is functional. As we approach the station at slow speed, the electrical supply to the Electro Pneumatic brake fails. Should the driver not observe the indication given by the EP supply lamp and commence to make his service brake application, his attention will immediately be drawn to the fault by the lack of distinctive EP contactor sound, and of course, the failure of any brake application to register. The driver must now react immediately by making an application of the automatic air brake. If he judges that the distance to run is now too short for a normal service application of the automatic air brake, he has final recourse to the emergency position on the brake controller. The selection of the emergency position at such low speed will bring the train to a dead stop in a very short distance, and this position should not be selected unless there is danger of collision.